From there? Yeah, okay. Okay. Okay, so let's start. So remember that what we've been doing, what we've been wanting to do, is to couple fermions to gravity. And what we did last time was to understand how fermions are described without gravity, just how Dirac fermions are described. And this was just flat space stuff. Okay, sure. And we found that the Dirac action should have the form d4x. This is in 4 dimensions. I gamma mu del mu minus n. Right. So this is what we did last time. So let's say last time. And then we asked the question, how do we couple this to gravity? So we tried a very preliminary naive thing of just putting root minus g here and making this a d mu. But then we were confused how to treat the field psi, because if you make this a d mu, should I treat this as a scalar? But it's not really a scalar, it's a spinor. So how do you couple? How do you understand that in gravity? So that was the confusion we ended up at last time. And I told you last time that the resolution to this whole thing is that you should think of Lorentz transformations in gravity as local Lorentz transformations. You can do a Lorentz transformation there, I can do a separate Lorentz transformation here, right? So basically the Lorentz transformation parameter, the omega, the capital omega from last time, becomes a function of the space-time manifold, okay? So then this becomes slightly more complicated. So in order to understand that more concretely, the fact that there are local Lorentz transformations, let me take a break from the Dirac equation and let's just do GR for some time. Let's understand how local Lorentz transformations work, what it means to be locally flat, Wheelbeins, co-Wheelbeins, all of that. Let's understand that. And then we'll come back and fix this problem. Okay. So last time I gave you this in order to set up this problem. And now I'll give you what we need to solve the problem. And next time we'll solve the problem. So first of all, so today we want to understand local Lorentz transformations, how to describe local Lorentz transformations, and orthonormal frames, which is to say, I can describe physics in my local flat space in a certain way, and I can choose an orthonormal frame in my local Lorentz flat space. That's the orthonormal frame. And I also want to, and with the orthonormal frames, which are basically Wheelbeins, co-Wheelbeins. And I'll do these, I will do in, I'll do in a certain fashion that you will see that you can write this for any D, but the Wheelbeins and co-Wheelbeins are called tetrads or Wheelbeins in 4D, and co-Wheelbeins are called co-tetrads, co-Wheelbeins in 4D. Okay, and they have other fancy sounding German names in 1D, 2D, and 3D. They're Einbein, Zweibein, Dreibein, etc. But we don't care about all that. We'll just do 4D and then general. So this is what I want to do today. So let's first try to understand the statement that locally everything is flat in GR. Okay. In order to understand the statement further, I want to revise. So maybe let me erase that. I want to revise how we think about vectors, right? What is a vector? Now, in the JR course, you would have learned that in this course, you would have learned that the vector is any V mu that transforms under a general coordinate transformation as del x prime mu under x going to x prime as del x prime mu by del x nu V nu. Okay, that's what a vector is. This is how, like, since like your first electromagnetism course with Griffiths or something, this is how you start defining vector. Vector is anything that transforms like a vector. A tensor is anything that transforms like a tensor, right? But this is a slightly weird way of defining a vector, because you're saying, so let's think about a vector in, say, 2 dimensions on the plane of this board. Let's say this is the vector I want to think about. Okay. So now let's say these are the coordinate system. These are your basis vectors, not coordinate system, but basis vectors, x hat, y hat. Okay. So let's say x hat, y hat, and let's say old. Okay. Or one may be better name. In these coordinate systems, in this basis, the vector has some components. Now I can rotate my coordinate system in a certain way such that I use, say, some x hat 2 and y hat 2. In this coordinate system, the vector has some different components. And that's what this equation is saying. But the vector itself hasn't changed, obviously. Just by you doing a basis rotation, you looking at this vector, if you look at it this way or if you look at it this way, the vector doesn't change. It's you that has changed, right? So this equation is telling you how the components of the vector has changed, not how the vector itself has changed. The vector doesn't change. The vector is just a vector. So how do you describe this vector without making reference to its components? Okay. And the simplest way to do that is to just say the vector is a V, which I will define as some V mu del V. This most of you should already know because vectors are really directional derivatives, right? So now you notice that V mu will transform in a certain way, del mu will transform in the opposite way. So this will just remain invariant under coordinate transformations. So this is the invariant way to think about a vector, because that's what this arrow means. Like whatever coordinate system you choose, whatever basis you choose, this vector will just remain this vector. It won't change. Okay. So such an object is what I will call a vector. And these V mu's are vector components. Now you might ask, what about, so this is a contravariant vector. What about a covariant vector? Okay, let's consider what about omega mu. So similarly, I want to construct an invariant thing which does not change whatever I do for an omega mu. Simplest way to do that is to dot it with something that transforms in the opposite way. But that something is very easy to see, it's just dx. And that's what I will call a covector. But not a covector, the correct name for it is the one form. That's the one form. And the components of the one form I will call, what are these called? Covariant vectors. These are contravariant vector components. Okay. So you should really think about vectors in this invariant way. Okay. But this is consistent with everything that you know already. It's consistent with the notion that a vector is something that transforms like this, because the components do transform like that. It's also consistent with the notion that the vector shouldn't change whatever you do to yourself. That's also clearly seen. Okay. So I want to like, I want you to think about vectors in this way for the next, preferably forever, but at least for the next 2 classes. So now you notice something very interesting, right? Which is that, for example, let's just do 2 dimensions. Let's just do 2-dimensional space, not space. Okay. For example, 2D space. I can write a one form as just say omega 1 dx1 plus omega 2 dx2. Okay. But this shows that these are components in this basis. I can change basis, right? I can, for example, write this as omega, say, prime 1 dx1 plus dx2. This is some basis. Let's say I call it omega a. let's say put a half here, and I write omega d as dx1 minus dx2. A and d are just average and difference. Just some name. Okay. I don't want to put a half there. That's difference. This is average. It's just some name. Omega A is just the coefficient of the average of the two coordinates. Omega d is just the coefficient of the difference of the two coordinates. I can of course do this. Now you can call this some coordinate. So you can call the coordinate y average as x1 plus x2 by 2, y difference as x1 minus x2, and this is what a coordinate transformation means, right? So omega A is the coefficient of ya, omega d is the coefficient of yd, dyd. Okay. Right? But then, so this is what a coordinate transformation means. So I have understood that like you can go from one coordinate to another coordinate. I've gone from some x coordinates to some y coordinates, and this is how the omega transforms. But physically, if you think about something physically, let's say I'm in gravity, I'm in a curved spacetime, which I am, okay? And I have some flat coordinate system. I have some x hat, y hat, z hat, okay? And some time direction. I'm free to choose whatever coordinates I want. I'm just choosing an axis. A basis is different from what coordinates are. You can still work in r hat, theta hat, e r hat, e phi hat, e theta hat. But you can choose coordinates x, y hat, x, y, z. You can differentiate er hat with respect to x. Nobody will stop you. You can still do it. So coordinates can be chosen separately from basis vectors, right? And that you can see here. For example, instead of choosing the basis dx1 and dx2, I can choose, I can also, we also have freedom to choose say some other basis. Let me call it e1, e2. There should be two basis vectors instead of dx1 and dx2. I can call say dx1 plus x1 dx2, dx1 minus x1 dx2. I'm free to do this, right? I can choose this basis for that one form. Similarly, I can choose some del 1 plus x1 del 2, del 1 minus x1 del 2, right? Nobody's stopping me from doing this. So the invariant way of thinking about vectors and forms is it's not just a change of notation. It already tells you something like this, which this component way wouldn't have told you, right? Secondly, notice that you cannot write this as some d of some f. So this is not a coordinate change. This is a basis change, right? I can use this as my basis and use Cartesian coordinates, or I can use this as my basis and still use Cartesian coordinates. Nobody's stopping me. Nobody can stop me because the physics doesn't stop me, right? So this is not a coordinate change. Anyway, so that's some quick crash course on vectors and forms. So since we have learned that you can take linear combinations of these infinitesimals and make them another basis vectors, this is the broad lesson I want you to take away from this, right? That components can be some coordinate components, which means that you should be able to write dx1, dx2 as the basis vectors and then write off the components. Those are coordinate components. But you can also choose another basis which are not coordinate basis, and you can read off components in that basis. So for example, e1x, so here e1x1 is 1, e1x2 is x1, e2x1 is 1, e2x2 is minus x1. I'm losing no information in writing it this way, right? If I give you my basis vectors like that, and if I give you that omega is this, is just omega 1 times e1 plus omega 2 times e2, then you can construct this, right? Okay, good. So now let's come back to the metric and try to understand this flat space business, locally flat space business. Already you can see the distinction between basis and coordinates. That's an important distinction. The distinction between frames and coordinates. You can be in your local res frame, right? But you can choose whatever coordinates you want. In this second problem in assignment 2, second or fourth problem, where you had an acceleration question. The accelerated observer, you can choose them to be in Cartesian coordinates, or you can choose them to be in spherical coordinates. So coordinates are different from frames. Right? A frame is the accelerated observer. When you tell me that, that's a frame. Radially accelerating observer, that's a frame. But the radially accelerating observer can choose whatever coordinates they want. Okay, that's this idea. Anyway, now let's come back to the metric. So with this, with what we have learned here, we can do something to the metric. You can specify the metric in a certain different way. So this you will agree is the metric, or the line element, which is written in terms of G mu nu, which is the metric. Excuse me. Use another chalk. Now, instead of choosing the basis dx1, dx0, dx1, dx2, dx3, let me choose some other basis instead of using the basis of one forms. Remember what a one form is anything that looks like this. Okay, that's just what a one form is. You don't need to know all differential form theory. I'm just telling you what a one form is. So instead of using the one forms, dx mu, let's use the basis EA. I will always denote one forms with this additional line. That will be a one form, and the components will not have that line. So EA is really a one form. So EA looks like EA mu dx mu. Okay. Notice here what happened. You had two one forms dx1 to dx1 dx2, and you went to two other one forms E1 and E2. Now E1 and E2 themselves have components. Exactly the same thing that's happening here. So this is really a what? This is a what kind of matrix? EA mu. EA mu is what kind of matrix? So here EA mu is what kind of matrix? 2x2 matrix. Right? If I write EAX as a matrix, and if I write that as 1, x1, 1 minus x1, it's a 2x2 matrix. Specification of that will give me the basis. Here EA mu is what kind of matrix? 4 cross. Let's do 4 dimensions. I mean, you can write it in DD. Nothing changes, but it's a 4x4 matrix. Such that, so I want to write it in such a basis that ds squared, okay, it's a basis one form. So dx0 is a basis one. Dx mu itself is not. Dx0, dx1, dx2, dx3 are all basis one forms. Yeah, it does not have an index. It doesn't really have an index. So okay, let me write that more precisely. Instead of choosing the basis dx0 up until dx3, right? Let's use something else. Yeah. I mean, what do you mean local function? It's a function. It's a function of x. Yeah. I'll show you an example. I'll show you like sphere Schwarzschild. Okay. So ds squared, I want to write it in this fashion. You will see why I'm using this complicated notation of bar underneath. That will become essential to us. But for now, just say it's some notation. I want to write it like this. Instead of in the basis of dx0, dx1, dx3, the metric looks like G mu nu. But I want to go to a new basis such that the metric becomes eta AB. It's just some flat metric. And you see why I'm doing this, right? Because I want to construct gamma matrices at the end of the day on a flat metric. Right? Now let me.
This form is defining basis at every point. Right?
Yes.
And the motivation to encode this information of basis at every point in a form is because we because we have this dx2 and dx2
Yeah, exactly. There's nothing else you can do, right? If you want to go from dx to something else, so that something else should be a linear combination of dx's, and that's what we call a one form. So it has to be a one. If it is equal to df, so for example, let's say here, since you asked this here, let me just answer that here. For example, if E need not always be df, okay? If EA is such that it's some dfa, so that means E1 is just some df1, E2 E2 is df2, E3 is df3, and so on. Then what happens? Then ds squared is simply eta AB, dfa dfb, right? So now if you go to the coordinates f0, f1, f2, f3, instead of choosing x0, x1, x2, x3, if you go to f0, f1, f2, f3, metric is flat. So that's a flat metric. So flat manifold is specified by the fact that these are called cotetrads, by the way. These one forms are called cotetrads. That the cotetrads are just D of something. Do you understand that? Okay, let me say that again. So let me give the name first. So these are called cotetrads, co-Wheelbein. Wheelbein tetrad, same thing, depending on what dimension you're in. In arbitrary D, it's called Wheelbein. In 4 dimensions, called tetrad. Okay. Now notice that when I wrote E, so coming back to your question, if E is D of something, okay, then working in coordinates f0, f1, f3, if you choose these as your coordinates, then you can see that ds squared is just eta AB, dfa, dfb. So I am saying I will choose my EA such that this is true. I will choose this is my choice of basis. So this specifies my choice of basis. So let me give you some examples. This might seem very abstract. So let me give you some examples of how do you sit down and construct this Wheelbein. Okay, it's called co-Wheelbein because these are called co-Wheelbein components. The inverse of these are called Wheelbeins. Okay, some historical meaning.
G can be diagonalized, right? We're absorbing that information into the
exactly. You will see that. Okay. Exactly what he said. G can be diagonalized, so you diagonalize it, and that diagonalization brings in a basis change, and you're doing that basis change. That's all. Similar thing is, so which is why I'm saying you should think of basis as separate from coordinates. You're not doing a coordinate change here, you're doing a basis change. So let me give you examples. There is the Dooster. And, let's think of examples. Let's do first S2. Unit radius 2 sphere, which is just defined as ds squared equals d theta squared plus r squared sine squared theta d phi squared. Sorry, not r squared. So now what is the choice of Wheelbein here? So here the eta AB should really be delta AB because this is a metric with no time component. So it just be delta AB. The simplest thing to do is just this. It's actually very, very simple. Wheelbeins are a very simple concept. It's just this. Nothing fancy. Obviously, ds squared is just delta AB. EA. Yeah. Right? Now notice that once you give the Wheelbein, you don't have to give the metric separately. The Wheelbein specifies the metric. Co-Wheelbein. I'll use Wheelbein and co-Wheelbein separately. Understand that co comes with a form and Wheelbein comes with a vector. Okay. Secondly, also notice, answering Ashok's question once again, is that you can write this as d theta, but you can't write this as d of anything. Right? Is that clear to everyone? Because if you could, let's say you could, then what does that mean? That means that sine theta d phi should be some del by del phi of f d phi plus del f by del theta d theta. That's what df means. Chain rule. Okay. So just equating components, just equating on either side, that tells you that sine theta is del f del phi and 0 equal to del f del theta. And these two equations are inconsistent because this tells you f is phi sine theta and that's wrong. Inconsistent. Okay. So this here is flat. It's not flat. Okay. Therefore, S2 is curved. S2 is genuinely. Okay. Let's write down the 2 by 2 matrix here. Okay. So here, for example, what is E theta theta? This is why I put the bar. You see, because E theta is a basis form. Now I can take the components of that. E1 is a form. I can take the component of that in the x1. So E theta theta is what? 1. E theta phi 0. There is no d phi. These are the components of that one form. E phi theta 0, E phi 1 phi sine theta. Therefore, the matrix E A mu looks like 1 0 0 sine theta. You can specify this matrix. And in just a minute. And in the non-diagonal case, when the metric here the metric was diagonal, so it is easy. When the metric is not diagonal, this matrix will just be the diagonal. Okay. Yes.
So let's say I specify some one form.
For a two-dimensional space.
For sphere, then that means that whatever one form I give, that should not be. I mean, I cannot express it in an exact form.
You know, you can never write both of them to be one exact. That's a theorem, right? I just proved that theorem. That if you write everything to be exact, the metric is flat.
No, but I'm actually saying the opposite. Since sphere does not identify the flat metric, then this is implying that there does not exist, cannot give two one forms of the sphere.
Such that
Both of them can be treated as exact forms.
Yes, that's true. That's the, you run this argument backwards, you get what you said. So this is an if and only if string. Okay, so it's a very simple idea. Should I do Schwarzschild? Schwarzschild I did last time, so I guess Schwarzschild. Okay, so Schwarzschild, for example, what will E be? So this is ES2, E Schwarzschild, A mu will be what? Very easy to write down, right? It's just that E0 should give you, let's say, the first term in Schwarzschild, which is -1 minus 2 gm by r dt squared. So I will write the first term here as 1 minus 2 g Newton by r square root. Second term as 1 over 1 minus 2 gm by r sin theta. Okay, so now we have a good handle on Wehlbeins and how they work. Now that we know this, and now that we also know that you can write vectors and forms in any basis, not just coordinate basis, let's see how they look in this Wehlbein basis. Wehlbeins we discovered from the metric, so let's see how they look in this Wehlbein basis. So let's consider question. Yeah, that will be a flat metric.
A sphere shouldn't have a flat metric.
Yeah, so for a sphere, you can't construct these two functions.
I can always consider functions and
You're saying let's consider function f1 of theta comma phi, f2 of theta comma phi, and let's do df1 df2, and then do eta ab df1 df2. I mean eta ab dfa dfb. That won't be the metric of a sphere. That'll be the metric of some other space.
metric in terms of df1 and df2 is not eta.
Yes, exactly.
Because the sphere is not. No, I'm not saying that. I'm saying using this one form, I'll write delta AB EA. That is not the same as BS2.
Yeah.
What do you mean? I'm constructing a metric.
Yeah, so that's not the metric for the sphere. Where in this process have you told me that it's a sphere? You have just considered a function of two variables, and you've just done dfa, dfb, eta ab.
I mean, I'm not saying that I have to get to that metric on the sphere. A sphere can have different metrics. Right?
No, okay, no, that'll be topologically a sphere. That won't be differential geometrically a sphere. So let's not talk about that. We're not doing topology. We can take this question out there. Confused with people. That's a confusing discussion. Ignore. Actually, but it is an interesting discussion. We'll take it outside. So that's the question. So let's come. So now we have already learned here that I can write omega in any basis, right? The form omega I can write in any basis. So let's take a different basis. Before doing that, so these are the co-Wheelbein components. Which is eta a e a mu. The inverse of this matrix, let e a mu be the inverse of e a mu. What does that mean? That basically means that e a mu e b mu is delta ab, or and e a mu e a mu is delta mu. That's what you mean by the inverse of the matrix. I'm just taking this matrix and taking its inverse. Okay, and the inverse I will call with e down, mu up. If you really want, you can call it e inverse of a mu. Okay, but it'll be clear from the fact that this index is down, the barred index is down, and the mu index is up, that this is the inverse. Okay. So e a mu I will call the Wheelbein components. Or the tetrad components. Okay. Now this tells you that, now let's take components of vectors and one forms. Let's now take this in this basis of one forms and vectors, components of vectors and one forms. So for example, what is a vector? A vector is anything that looks like this. Let me first do this for a form, then let me come to a vector. A form is anything that looks like omega mu, dx mu. But I can write dx mu in terms of E, right? Because EA, I told you, is EA mu dx mu. But EA down, mu up is the inverse of this matrix. So I can act that on both sides, and so this will become identity. Right? So multiplying the above equation by E, say, A nu, okay, by using this, or say this. So this becomes what? E A nu E A will be dx nu. Is that okay? So I'm just basically going from, so here I went from x1, x2 to e1, e2, but I can also go from dx1, dx2. Sorry, I can write dx1, dx2 in terms of linear combination of A1 and A2. So this x1 will go down and so on and so forth. So that's just the inverse of this matrix. And that's that. Okay. So if you put that in here, what do you get? You get omega is omega mu dx mu, but dx mu is just EA mu EA. Okay. So in the basis of these one forms, I will define the coefficient where omega A is the coefficient. So far, everything might have seemed like a change of notation. You're just going from some mu indices to some AB indices at some bars. But now you begin to see that the A indices and the mu indices are not talking to each other. They're standing separately on equations. For example, this equation, the A indices match on both sides and the mu indices are contracted. If I put a V mu here, there will be V mu will be there also. So the mu indices and the nu indices should match separately on either side of the equation. Okay. What the Wheelbines do is actually give you a new structure on top of the spacetime structure. Okay. This will become more and more clear as we do a little more algebra, but I'm saying that I can define a component of the one form in the basis of the Wheelbines, and this is that component. Okay. Similarly, I can define the component of a vector, say VA, by just using the inverse of this matrix. I can just do EA mu V. At this point, I'm just exploring the Wheelbines and co-Wheelbines. I defined them, they look nice, they give you an alternate description of the metric, and now I'm just sitting down and exploring them. Okay, what all things can be written in their way, what do the components look like in them, etc. Okay. So now notice the important fact, this is all towards doing spinors, right? Because notice that these VAs are components in a local orthonormal frame, in a local flat frame, because EAs are basis for a flat metric. So this VA is a component on a local frame. Now if you do d mu of this, the d mu should act on this as well as that. So it's no surprise that psi in the spinor in the Dirac equation, if you just do d mu, you should not just do d mu of psi, because the psi has components in the flat space, in the local flat space. It's a spinor in the local flat space. Does not have components, but it's a spinor in the local flat space. Okay. So anyway, so that was just a quick reminder that we're still doing that. So that's how you take components. Now let me show you a different thing. I already showed you here that if I give you this matrix, the metric is specified. Let me just write that down more generally with this notation that I've introduced. Now, also remember that when you're in a local flat space, you should have a local Lorentz transformation degree of freedom. So this formalism should already start showing you that. Okay. So that's when this formalism takes on a life of its own. It's not just components, it's not just change of notation. It tells you something new, that there is a local Lorentz transformation degree of freedom, which we'll see in a moment. So we have introduced co-Wheelbines and Wheelbines, and orthonormal frames are just these A's, EAs, EMUs. So we are done with that. Local Lorentz transformation will come to. But before that, let me make clear the fact that that matrix giving is the same as giving the metric, because ds squared is g mu nu, dx mu, dx nu. Okay, which is equal to eta AB, EAB. But EAEB itself is EA mu, EB mu, dx mu, dx nu. Comparing these two equations, we basically get that the metric is really some dot product of the tetrads. And this is a very powerful relation. So box it up. We'd have to use it again and again and again. So what it tells you is that the AB indices act separately from the mu nu indices. The AB indices you should raise and lower with eta. The mu nu indices you should raise and lower with G. Okay. And they have a life of its own. This has a life of its own and this has a life of its own. Okay. I can also write the inverse of this equation. I can write eta in terms of G. Let me also write that up because that will also be very powerful. That's basically using the same equation. You write G mu nu, dx mu, dx nu. I mean, you can just matrix invert here, but let me just do it here. It's just eta AB, EAEB. But we found that dx mu, what is that? Dx mu is just something times E. So this is equal to what? This is equal to G mu nu, E A mu. I'm writing these equations, I'm writing these relations down so easily because I know that the Latin indices and the Greek indices transform separately. So I can just write them down directly. And now you argue that A, B are just some bases. So the basis vectors are equal on both sides. So you get eta AB equals G mu nu, E A mu. Everything is consistent. So far, nothing's wrong. Everything works out. So far, so good. So you can write the metric in terms of the tetrads. Given the tetrads, you can write down the metric, or given the co-tetrads, you can write the metric. Same thing. Okay, so that's the long story about tetrads. Now we have learned tetrads decently well. We know what they are. We know what they give, which is a flat space metric. We know some examples, S2 Schwarzschild. And we know that the metric can actually be specified in terms of the tetrad. So the tetrad is an alternate formulation for gravity. Instead of talking about the metric, we talk about the tetrads. Same thing. You can translate with this equation very easily. Now, what I'm going to say next is what really tells you that there's something entirely new in tetrads. Let's take another look at ds squared equals eta AB EA EB. Okay. If I transform, if I Lorentz transform EA, that is EA going to some lambda A B EB, right? So I erase the example, but basically what I'm saying is that, for example, there are two one forms. I do some rotation between them. I write the new E theta as some E theta plus E phi, new E phi as some E theta plus E phi, some linear combination. That's what this is. Lambda AB is some linear combination. If I do this, then ds squared is just the same thing. It remains invariant. Right? Because that's what a Lorentz transformation is. Lambda transpose eta lambda is just identity. Sorry, lambda transpose eta lambda is, yeah, eta. What I'm saying is that eta AB, lambda A C, lambda B D is equal to eta C. Right? That's how you define a Lorentz transformation. A Lorentz transformation is defined such that this is true. So you discover local Lorentz transformations. And now once we have the local Lorentz transformations, we can play the same game of spinners that we played last time, which is to just construct gamma matrices, but all the gamma matrices will not have mu indices anymore. They'll have A bar indices. Right? Because you should construct the gamma matrices in a flat frame, and this is the flat frame. And the Lorentz transformations, this S mu nu that I wrote down last time, omega mu nu S mu nu, instead of using S mu nu, you should use AB, because all of that should be done in flat space. And this is the flat space. So that's we have discovered. Why am I calling them local? Because this can be a function of x. Right? So I'm not doing a global Lorentz transformation where I'm just doing the lambda for everywhere in spacetime, just one lambda. That's of course already there. That's always there. That's what we did last time. When we did spinors last time, the lambda was not a function of x, which answered Atharva's question that why didn't you differentiate the lambda? Why didn't you differentiate this capital omega? Right? But here now, the lambda becomes a function of x. And even with the function of x, the metric remains invariant. Local Lorentz. Now we have a flat frame, an orthonormal frame, and on top of that orthonormal frame, we have also discovered the Lorentz transformation. Now playing the game of spinner should be easy. Okay. So now I'll pause for 2 minutes and note if there's something I'm forgetting to say. Yeah. Just a minute. Yeah. So remember that last time when we did this, when we wrote this down, how did psi transform? Psi transformed as exponential I omega mu nu, I over 2, S mu nu, psi, right? This was not a function of x. I told you this was just some boost and some rotation. It was just some numbers. I give you velocity, I give you an angle. And S mu nu was just commutator gamma matrices. Right? S mu nu was just I over 4, gamma mu, gamma mu, gamma mu. Right? So this is clearly not a function of x. These are just some constant matrices. And this was also not a function of x. So when you did this del mu, it didn't act on all this. It just acted on that. Right? And then we had to do some work to find out what is the invariant combination, and we found that this was the scalar. But now notice that at every point in space-time, you have a freedom to do a different Lorentz transformation. At x1, I can do some Lorentz transformation, which is basically like saying, I'm sitting here, I can do some Lorentz transformation. You're sitting there, you can do some other Lorentz transformation. But here, everybody has to do the same Lorentz transformation. Because if you're in completely flat space, you and I and everybody else has to do the same Lorentz transformation to rotate the flat space. But here, since we are in curved space-time, I can do a different Lorentz transformation at each point in space and time. So then this lambda, this omega will become a function of x. So then this del mu will start talking to this omega. And then this won't be invariant anymore. Right? Which was the problem last time. So you have to add something to make it invariant. We'll see what. So you'd have to define a correct covariant derivative of a spinor, accounting for the fact that this is a function of x. We'll do that probably next class because there's some more stuff to do this time. But that's the idea of a local Lorentz transformation. Local basically means that at every point in space-time, you can do a different Lorentz transformation. Okay. One thing I forgot to say is that if you look at the tetrads, for example, in this 4-dimensional example, it has a total of 16 components. This is a specific example, but in general, it has a total of 16 components. And I also told you that the metric can be found directly from the tetrads. But the metric has only 10 degrees of freedom, 10 independent degrees of freedom. So 16 independent degrees of freedom. So where are those 6? I've already given you the answer. Yeah, right? Because I'm free to do EA going to lambda A B EB, and that won't change the metric. Right? And there are 6 Lorentz transformations. So I can fix 6 of the components of EA just by doing a Lorentz transformation, and the rest 10 are the metric components, which makes sense. Awesome. So what have we learned? We have found Weyl-Binds, co-Weyl-Binds, and we see how they describe an orthonormal frame locally. And we have found these local Lorentz transformations from them. And I also told you that this is some basis change, so you can put vectors and tensors in that basis. Now let's come to the most interesting part of today, which is if you can take components with respect to this basis, what about the derivatives of these components? So notice another important fact is that EA mu, so the tetrads, transform as a vector as vector components under the mu and transform as a form in the local Lorentz transformation. Okay. So this under a local Lorentz transformation, which I will call LLT, transform as lambda AB EB mu. That's just this. I'm just writing EA mu dx mu, EB mu dx mu, cutting off the dx. Right? But at the same time, E is also under a coordinate transformation, general coordinate transformation, transforms in a familiar way, right? Because it has a mu index up. So it has to transform like del x prime mu, which is going to x prime over del x mu. Okay. Okay, remember that. So now, how do you take derivatives of frame components? In particular, covariant derivatives. I will tell you what covariant means in a moment, but let's recap what it meant for before all this Bard indices came into the picture, before all these Latin indices came into the picture. How did we define a covariant derivative? Let's say I wanted to define it for a form, for a covariant vector. We just defined it as some del mu minus gamma alpha mu, right? And we defined it in such a way that this under a coordinate transformation transforms like a 0 to tensor, right? Transforms like a 0 to tensor. And that's how you defined a covariant derivative. Now I'm asking, what about d mu? Instead of writing the components in mean in the coordinate basis, let me write the components in the frame basis. Right? I defined this for you earlier. Right? Omega A is omega mu. Now, how should I define such a covariant? Let's use another symbol because this is a covariant derivative for some other component. So how should I define this? Any ideas? Yeah. Right. Not invariance. Yeah. So usually we define anywhere in physics, case theories or here or in general relativity, you define a covariant derivative as something that transforms nicely, as you're saying, right? When you took a covariant derivative of this vector, you said since there are two indices, I want this to transform like a 0 to tensor, like something that has a mu nu index, like a t mu nu. So here, notice that I have two different kinds of indices, but I know how each of these transform. This index transforms under a local transformation like this. This index transforms under a GCT like this. So I want to demand on this covariant derivative the property that this whole thing transforms like this as well as that. So we demand that d mu VA transforms as a contravariant vector in the mu components, in the mu indices. Sorry, covariant vector. Yeah, which is why I don't like that notation. It's confusing. As as well as the A bar indices. And the simplest way to do that is something that you already know. No, LLT is separate. So general coordinate transformations, just let's do a counting. Okay. General coordinate transformation, how many are there? 4. You can take four space-time coordinates, t, x, y, z, and transform them independently. So you have 4 general coordinate transformations. How many LLTs are there? I did a counting. It was 6 because there's lambda AC. Lambda AC has to satisfy eta lambda equals eta. So that has 6. So that's a total of 10. And that's the number of degrees of freedom in the metric. So that counting has to match. So LLT can't be contained in C. And this is why you have to introduce the form, the Vielbeins, because otherwise you won't see the local Lorentz transformations. So if you want to think about gravity as a gauge theory, it's a gauge theory of LLT and GC, where you get 10 gauge fields. Anyway, so that's a digression. Yeah, so it has to transform under both of these. Simplest way to do that, let's pull this up. That contains everything. But most people also say that wrong. Most people say, for example, one class of people say that gravity is a gauge theory of LLT, and another class of people just say that gravity is a gauge theory of GCT. Both are wrong because the counting doesn't match. I mean, at least to me, it seems wrong. Maybe there is some very probably some names. I don't buy that distinction. Because to me, I think of gravity, like let's not go into the digression. Let me do this. Or let me just say, to me, I think of gravity as I'm sitting locally, things look flat to me. But maybe let's consider the possibility that if I start exploring more and more, things will start becoming curved. Things will not look like flat space anymore. So I gauge that local Lorentz transformations. But on top of that, I also have the degree of freedom that I can choose whatever coordinates I want in these 4 directions. So I have a gauge transformation in that also. So if I gauge all these 10, what I get is gravity. And that you can show. That if you take the gauge fields for LLT and GCT and write down a gauge invariant action, you'll end up at Einstein-Hilbert. But anyway, ignore. Quick digression. Anyway, yeah. So how do you do this? You want this to transform as a covariant vector in this as well as that. Simplest way to do that is to do this. I knew this question would pop up, which is why I said people think about this very differently. This is how I think about it, and I think this is correct. And I think, anyway, let's concentrate on trying to do something practical. These are all some like abstract ideas, which probably not be useful. Anyway, so this, do you agree with this? This is the simplest way to achieve both these things that I said, because this obviously EA nu transforms as a lambda AB, so it transforms correctly, nicely under these A index. And since this is contracted, and these are just all nice mu tensors, this just has a mu index down, so that transforms like covariant vector. This will be like, if you forget about this index, this is just something like that, and that obviously transforms as a covariant vector because I've used the covariant derivative. Okay. Now let's write this down explicitly. And in writing this down explicitly, we'll find a new quantity. And that quantity is what will enter the Dirac equation. Okay. And probably I'll stop. No, I can't stop. I have to do something more. E a nu d mu. What is v mu? V nu is really E a nu v a. Let me use b. Remember that I'm taking a covariant derivative with respect to the frame component. So I want to write the answer in terms of frame components, which is why I wrote this in terms of that. So this becomes E a nu d mu E b nu vb plus E b nu d mu vb. Remember that this is the inverse of that. So that gives you delta AB. So it gives you E a nu d mu E b nu times VB plus d mu VA. And I want to write this in the usual way we write covariant derivatives. And notice that this does not have any index, any spacetime index. So d mu is just del mu. Okay, and I want to write this in the usual way we write covariant derivative, which is del mu plus some gamma, right? So I will write this as del mu VA plus. Notice now that the other thing should have a mu index, but it should have an A index as well as a B index to contract with the VB. So now this looks like what? Omega A B mu is E A nu d mu E B. More explicitly, E A nu del mu E B nu minus gamma mu nu rho E rho. And these are called the Ricci rotations. They're called many different names. They're also called, so omega AB without this mu is called the, which is basically saying omega AB defined as omega AB mu dx mu. Okay, this is called the spin connection one form. Both are just some names. Most people just say the spin connection. Nobody really says. I mean, I haven't heard anybody say Ricci rotation coefficients, but Wald calls them Ricci rotation coefficients, the components of the spin connection. And they're called a connection because they are a connection, as we'll see in a moment. Transforms like a gauge field. Anyway, what have we learned? We have learned that once you've discovered Weyl-Binds and orthonormal frames, you can put vectors and forms in their basis. And you can also take covariant derivatives of those components. And in taking the covariant derivatives of those components, you discover a new connection. Just like you write usual d mu, where is they write a usual d mu? Yeah, usual d mu write as del mu plus some connection. This is called the Levi-Civita connection, or the Christoffel symbol, same name. This is called the Levi-Civita connection. Similarly, when you write it like this, you discover the spin connection. Now I forget how it's conventionally defined. I don't know if people put a minus sign there. Let me just check. No, it's fine. So okay, so I should note that some people actually put a minus sign here because they want this equation to look exactly the same as that equation and define the omega with a minus sign. I'll not do that. This looks nice because this expression is very memorable. I don't want to put a minus sign there. Again, notice that the Latin indices and the Greek indices are completely separate. So if you knew that this had a covariant derivative, obviously there should be a del d mu, and these indices should match. So you should put something like this, and you should put something like this, and these indices should contract. Okay, so you should start thinking of the Vierbeins and their components in this way, that everything should match. The Vierbein components should match on both sides of an equation, and the frame component should, and the coordinate components should match on each side of the equation. Great. So we are actually very, very, very close to writing down the Dirac equation correctly. But in order to do that, we need to know how this transforms under the LLT. Because we seem to have found a new connection, and we want to know how it transforms. Right? In GR, when you write down Levi-Civita connection, you first discover that it does not transform like a tensor. It has some additional component, coefficient, additional term, and that additional term is what cancels something that comes from the partial derivative. And so this is covariant. Right? So I want to do the same calculation for this one. I want to see under E going to lambda E, how does omega transform? Okay, and that will be a very interesting calculation. Let's do that. Maybe after that I will stop. And next time, with all of this language that we have set up, next time I can just directly write down the answer for the Dirac equation in curved spacetime. This to that. Notice that this does not have any index, the Latin index. So this really transforms like a scalar under d mu. This is a scalar under general coordinate transformation. This is something new that which is the answer to your question, that these two should be treated separately. These two are two different things, right? Those indices transform completely different from Latin and Greek indices transform completely differently, which is what is seen here. This transforms like a scalar under GCT, but transforms like a one form covariant vector under LLT. So now, how does omega AB, omega AB transform under EA going to lambda AB? This is the question I want to answer. And that you can just do directly, right? You have an expression for omega in terms of E, just transform it. I'll do that explicitly. Transforms as. So this will transform to lambda. So you get a lambda AB. Remember that lambda now is a function of x. That's the whole point. EB mu del mu lambda BC EC mu minus mu lambda BC EC. Is okay? Hmm? Uh-huh. Oh, you're saying I have too many B indices. Yes. D say. Or C. I'll use D here. Right? Now indices look great. Okay, let's do this differentiation. Oh, yeah. So lambda AC EC mu. This gives you two terms. Remember the lambda is a function of x again. So this gives you lambda B D del mu E D mu plus del mu lambda b d e d nu minus gamma rho mu mu lambda b d. I think I should pull this board up because I don't really have space to finish this there. So, and this gets blocked, so wait for a minute. So really this is a finds the spin connection. Pull it up. Terrible. Okay, so we have seen all this, so maybe I should just erase this. So what have we found? Omega A B mu transforms as lambda A C E C nu lambda B D del mu E D mu. This last term is what I wanted. It's gone. Minus lambda rho mu lambda B D E D rho. Oh, with another lambda, right? There's a lambda A C, and then there's a lambda B D, and then okay, and then there is the del mu lambda term, which is plus lambda C E C mu. Just a minute, lambda B D E D. Yeah, what? Yeah, E C. Okay. Now, first line is really just lambda A C omega C D mu times lambda D D. Right? Because notice that EC nu del mu ED nu is the first term of omega CD. You see this? And then minus gamma E is the second term. Yeah. Make sense? And the final term, here nu contracts. So this gives you, these two are inverse matrices. So this gives you delta CD. So this gives you plus lambda A C, D is just C, del mu lambda B C. Okay. And for those of you who have seen non-abelian gauge theory, this is how gauge field transforms. And for those of you who haven't seen non-abelian gauge theory, this is the generalization of A mu going to A mu plus del mu lambda. So this is a gauge field of the local Lorentz transformations. Okay. Let me write this a bit more suggestively because I can't remember it this way. So this is correct. I mean, omega A B mu transforms like this. So this is the answer we wanted. And most importantly, notice that omega transforms in such a way that it has a del mu lambda. Okay. And when writing the Dirac equation down, this is exactly the same problem that phase does, right? You had a del mu, but then you had a del mu of psi, and then the psi transformed as like an exponential with a lambda, but then the lambda was a function of x. So it'll give you a del mu lambda. But already you can see that maybe you can construct a covariant derivative with this connection instead of a del gamma connection, instead of a Levi-Civita connection. I can use a spin connection and get rid of that term. And that's what we'll do. The usual idea in gauge theory, if you may. Lambda, you mean? Lambda is the gauge group, which is the Lorentz group element. So this is the gauge field for SOD, 1. And the Wehlbeins should be thought of as the gauge field for the Poincare, for the translations. And so the full gauge theory is the gauge theory of Poincare, which is ISOD, 1. That's just for him, or whoever else knows what I said. So I don't like to write it like this. I like to write it slightly differently, which is by noting the fact that Lorentz transformations have this curious property that lambda inverse dB is lambda PD. You can check. This seems familiar. Do you remember? You can sort of. Do you want me to show this? I mean, it's a quick thing. Okay, fine. Yeah, I'm there. You have to get this. So then omega transforms very nicely, which. So since I've really given you the answer, you can ignore what I'm going to write now. Okay, if you don't want to write it in this language, because I want to write it in a pretty form. Omega C D lambda inverse dB. Now the indices just go in a chain. Plus lambda is C del mu lambda inverse C. Okay. And now if I put a dx mu and make this a spin connection 1 form instead of that, this becomes an omega 1 form. This becomes an omega 1 form. And this d mu becomes a d. This is the usual way we write gauge transformations. We say A goes to UA U inverse plus U D U inverse. That's what's happening, but there are more indices because there are many gauge fields. There are 6 gauge fields. So this is really a gauge transformation. Ten minutes ahead of time. So let's see. Yeah, actually, I do want to show some things more about it that I will use next time. Okay. So what we have ended up discovering is that if you write things in Wehlbein components, I mean, I'm repeating this probably for the 5th time, but when you write things in terms of these Wehlbein components, and then you take covariant derivatives, the connection you should be using is not the Levi-Civita connection, it's not the gamma, it's not the Christoffel symbol, but something else called an omega, little omega. Okay. And this little omega transforms in a very nice way, very interesting way under local Lorentz transformations, because it gets a del mu. So it gives you a clue that this is what you should use to fix the covariant derivative in the spinner. And that's what we'll do next time. I'll give you an answer and then we'll just sit down for an hour and do a calculation and check that the Dirac equation is invariant under these local Lorentz transformations. But since we have some time, I also, this I was going to leave as an exercise, but I can show it to you. Yeah. You were going to ask something? Okay. Sorry. One interesting property of these spin connection coefficients is that omega A, B, mu. Remember that you raise and lower frame indices with eta. So this is defined with eta is equal to minus omega B. Okay, and that's easy to prove. And by the way, you should I did this for a contravariant covariant vector, but you can do the same thing for a contravariant vector VA up. Okay, and then you can check that the same omega comes there also. But let me check this now. So this is the antisymmetry of the spin connection form. And this will be the consequence of the fact. Oh well, let me just do it. You'll see why it is a consequence. So omega AB mu is defined as E A mu B mu E B. Right, or let me just do this slowly if you're confused. This is defined as eta A C omega C B mu. And this I've already told you what it is. Or wait, maybe I should do this. Okay, which index is up, which index is down? A is down. Okay, so let me do A, B, C, C. Okay, and I've told you the definition of what is there. So then this is just eta. Eta, remember, is a constant matrix, which is minus 1, 1, 1, 1. So this is E A mu B mu E C mu by the definition, which I wrote down there. And I'm writing it down without looking at it because remember, all the indices must contract. The only way to do that is to do this. All the indices must contract and it should be covariant. It's covariant. Eta B is constant matrix, so it just goes inside. So I can just bring this down. B. Okay, let me just keep it outside actually. Maybe this is useful. Now you use the fact that this is eta BC. Then you take this d mu outside, do an integration by parts, and you get, not integration, I'm not doing an integration, minus EC mu d mu E. Is okay? I'm just using Leibniz rule to rewrite that. And this d mu, what is this? Because this is eta AC. Did I erase that? Yeah, I erased that a long time ago. This contracts and that gives you delta AC, sorry, not eta, delta AC. And d mu of just delta AC is 0. Delta AC is just numbers, d mu is 0. So this gives you minus eta BC EC mu d mu EA. And so this is equal to minus E B mu d mu E A mu. Now since the metric commutes with the covariant derivative, I can pull this index up and that index down. And that's just minus omega B. This formalism is not just useful for spinners, it's actually very useful to read off components of the Riemann tensor, Ricci tensor, and so on. I will not tell you more about it. I mean, maybe next time if I have time, we can discuss it. But as an exercise, so we are out of time now, but as an exercise, I leave the following. show that dE omega AP wedge. This is for those of you who know wedge products and exterior derivatives and so on. If you don't know this, completely ignore because you're not going to use this I'm not going to use this next time. And since you all know differential forms, I should tell you that people here at least know differential forms. I should tell you that if you take a d of this equation, what you get is first Bianchi. And you can write down some other equation from here, which if you take a d of, you'll get second Bianchi. So first Bianchi and second Bianchi, I told you at some point was a consequence of Jacobi, but then now it's also a consequence of d squared equal to 0. So Jacobi, Bianchi, d squared equal to 0. All of them are related. Some very deep fashion. And that should not be surprising because Bianchi is like saying what? Bianchi is like saying you take some closed derivative of this Riemann tensor, it should be 0. That's like saying in space-time you go this way and then 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 you cover a full cube, okay, and then compute the curvature. Okay. But that's like staying at a boundary of a cube. But boundary of a boundary is 0. That's like saying del squared equal to 0. Dual of that statement is d squared equal to 0. Obviously d squared equal to 0 should be related to Bianchi. Yeah, I mean, there are lots of many fun, deep things that you can explore here. Because once you write everything in forms, there are many new structures that come out. But this is just a fun exercise for those who know. Forms. From here, actually, so if you for those who know forms and gauge fields, I told you that omega is really a gauge field. From omega, you should be able to construct a gauge field strength, right? I mean, we are out of time, which is why I'm saying extra stuff for those who know. You should be able to construct gauge field strength, and the gauge field strength will look like this: d omega plus omega wedge omega. Right? That's the analog of F equal to dA. But when you have non-abelian gauge theories, F equal to dA should be corrected by some A wedge J. This is that A wedge J. It should be A, B, A, B. And then now once you have the F, what do you do in electromagnetism? Sorry, CCB. And once you have the gauge field and the gauge strength, what do you do in electromagnetism? You write down an action. You write down F wedge star F because you have to do star F. So on, you do F wedge star F and that gives you an action. Here also, you can take this R and write down something that's completely invariant. What you end up with is gravity. What you end up with Einstein gravity. So this is a completely different way of looking at gravity, where you say, locally everything looks flat to me. Maybe if I go globally, things will curve. So hence you introduce tetrads. And from tetrads, you do all this business, you encounter this. So then you have tetrads E and the omega. Once you have the E and the omega transforms like a gauge field, E transforms like a one form. Can you put E and omega together to write down a Lagrangian? You write down a Lagrangian and you end up with gravity, end up with Einstein gravity. But anyway, that's just some fun exercise. If you have time, you can have fun doing that. But our intent is, of course, to write down the Dirac equation and show that the Dirac equation can be written down nicely, it transforms correctly, and so on and so forth in curved space-time. And we have all the ingredients we need. Last time we learned what the Dirac equation is. This time we have set up all the ingredients we need to couple it to gravity. Next time I really don't have any work to do. I can just write down the answer for you, and checking the answer will take like 3-4 boards. But I'll probably not check it. I'll ask you to check it because you just have to sit down and explicitly do a calculation. But yeah, we're basically done. So thanks. Any questions? Yeah.
You said that omega is like HP for the local.
Yes.
And ES will be the.
Not like they are. They are.
ES will be the translation.
E's will be the gauge transformation, gauge fields for the. Just a
Is it over?